Hello, everyone. So this is passage 4 of the Chem Phys section of JackWestin's fifth practice exam. So let's jump right in. Hopefully now we are getting to the flow of highlighting and what we should highlight and what we shouldn't, and how we should go about tackling questions. And let's see what they have for us today. All right. Power generation. That's what we're talking about. Power generation during exercise. So can be measured to assess physical performance. In a healthy adult, the power generated varies with exercise intensity, as shown in figure one. So figure one is usually I like to read the captions first, relationship between power generation versus time. Always the thing that comes after the versus is your independent variable during mild exercise. Dash line for mild exercise and heavy exercise is the solid line. Health, yeah. So basically, power generation increases at a higher or faster rate in those doing heavy exercise versus those doing mild exercise, which makes sense. You need more power to move your body, right? During exercise. Let's read the rest. The energy required for muscle activity during exercise is supplied by glucose metabolism. So energy required is supplied by glucose metabolism, right? The rate of glucose uptake, G, by muscles can be related to the power output using the equation one. So I just need to know what G is, and I need to know what P is. P is power out, right? And those are be found in equation one, where K is the proportionality cost constant, right? I need to know these. And this is the efficiency factor. Is the intensity factor. These are very good things to know. I'm highlighting a lot because I just want you to see things you should be looking at, right? Which could be a value between 0 and 1, where 1 represents this might be important. I don't know. Right? P is equal to K. G, they've given us the equation. Total energy expenditure, E. We need to be able to define all our variables, right? And time as T can be calculated. Energy is equal to power multiplied by time. So energy, the total energy expenditure is equal to the power output multiplied by the time. The introduction of a drug that enhances glucose uptake by increasing the efficiency factor can significantly affect the glucose metabolism rate. So if you introduce a drug and this drug happens to enhance glucose uptake, and how does it enhance glucose uptake? It increases the efficiency, right? That drug can significantly affect glucose metabolism rate. They didn't tell us how, but it just said this is something to take note of. Researchers developed a drug with a half-life of 120 minutes that increases K from 0.2. So what does this drug do? Remember, first encounter now, encountering a drug now. This drug is increasing our K from 0.2 to 0.3. You know what? Let me just highlight this. Right. Now it looks like a lot. I mean, I did a lot of highlighting in the middle here just to show you things to take note of. You don't necessarily have to highlight them. The bolden P and G would be your highlight, so you don't necessarily have to put yellow there, but just to show you things that you need to know the variables anytime there's an equation, right? The first question, what is the relation between G and T? This is really the question they're asking, given that the efficiency factor and intensity factor equal 0.5. So both efficiency factor and intensity factor equal 0.5, right? So now let's see. In our first equation, we have G there, but we have no T. In our second equation, we have T, but we have no G. But in both equations, we have P, right? The power output. So what we are going to do is we are going to rewrite both equations and make P the subject of the equation. In the first equation has already been done, but in the second equation, our P is going to be equal to E, total energy expenditure, divided by our T, right? So now what we can actually do is we can insert this P into the first equation. So what do I mean by that? We get E divided by T is equal to K times G times 1 plus this constant times I. So the question says that efficiency factor and intensity are 0.5, right? Now, I mean, to be honest, they didn't say, well, it could be zero. Both of them are equal to 0.5 if you have sum them up, or they are equal to 0.5 each. I'm going to assume each because that's the only thing that makes sense because they're actually multiplying each other in this equation. Right? So now that we know that each of them has 0.5, we have our equation down. I'm now going to solve and make G the subject of this equation, right? So E, that'll take please. E divided by KT, I'm just bringing this down. It's going to be my G multiplied by 1 plus, and 0.5 times 0.5 will be 0.5, right? And this gives me E divided by KT. It's going to be G 1.25. From here, I don't even need to think. I'm looking for 1.25 here. And the reason why D is not the answer is because from when I rearranged, you see my constant is a denominator. It cannot be a numerator, right? So then this is going to be my answer. My answer is going to be B, right? All I needed was the 1.25. The rest of it, I'll figure it out. Right? All right, so that's great. Let's move on to the next question. Assuming the efficiency factor and intensity factor were equal, so they don't change, the glucose uptake of a healthy adult at 30 minutes before, so 30 minutes of mild exercise with no drugs is equal to, so 30 minutes of mild exercise with no drugs is equal to, so let's write that down first, right? What is the glucose uptake of a healthy individual at 30 minutes of mild exercise? So my P is going to be K, G is what we are looking for, multiplied by 1 plus constant intensity, right? So this is for my healthy individuals. So this is my healthy, no drug. Everything on the left. And looking at my answer choices, I needed information from there because as I was doing it, I will be able to know what I'm comparing it with. This heavy exercise with drugs, right? So heavy with drugs. Forgive my handwriting, this is mild. Great. So this is also going to be P kg 1 times all of that. Right. Now I can cancel these out because it remains the same. So cancel these out. And just focus on my P, K, G on both sides. K, G, right? So I have the G for my mild, no drugs, G for my healthy with drugs, right? Another piece of information we know is that K increases from 0.2 to 0.4 when there's drugs, right? So K is going to increase to 0.4 here. So it's going to be 0.4 G. And there's going to be 0.2 G. This is times G. Comparable, because that's what I'm supposed to do. Now, at this point, I have everything set up. All I need is my P. To be honest, I've not seen most MCAT questions having you draw lines on a graph to detect, but they definitely want you to estimate, right? Or guesstimate. So I'm going to just draw this line as straight as possible. And it's like 110, maybe even 100, but let's go with 110, right? That's for heavy exercise. And for mild, we'll go with like a 70, right? That sounds fair. And a 70, right? So that being said, P for mild healthy is going to be a 70, and that is equal to 0.2 G. And then our P for heavy and drug is going to be 110. That is going to be equal to 0.5 G, right? So in other words, our G for our mild is 70 divided by 0.2. And the G for the heavy individual with the drugs, like with the drug that they gave to the person, is going to be 110 divided by 0.4. I can round this to 100. If I round it to 100, then it means it's going to be probably like 250-ish. And with 70, 2 goes into 70 35 times. So it's probably going to be like 350-ish, right? So in other words, from mild to someone who's doing heavy exercise with the drug, the number increases from 250 to 350, which means that looks more than probably around more. There's definitely more than 25%, much closer to a 50%. So the first two answers will be out because this is 25% less. Anything that says less is out. But between 25% and 50%, I believe 50% of 250 is 125, right? If I add 125 to 250, I get 375. So this is more like a 50% increase. So again, when it comes to MCAT, as long as you are close, that's probably your answer, right? As long as you are close, that's probably your answer. All right, let's do 20. After 6 hours, what percentage of initial amount of drug will remain in the person's body? So again, I was doing red flag and green flag in my head. I was not saying it, but for this question, I'm going to say it so that you know how to say it. After 6 hours, they've given us what percentage of initial drug. From here, the only information about the drug we have is the half-life. The half-life is a green flag. It's something that they've presented in the past. Right? What don't we know? What we don't know is the formula for half-life. The question is, do we need that formula? Or let me say the concept of half-life, the definition of a half-life. So the definition of a half-life basically is the time it takes for half of the drug to go away or half of the radioactive material to go away. That's a simple definition, right? So if I have a half-life of 120 minutes, it means it takes 2 hours for half of the drug to go away. In other words, after my first half-life of 120 minutes, after 120 minutes, which is going to be 2 hours, is going to be, I'm going to be left with 50% of the drug. If I wait another 2 hours, which makes a total of 4 hours, I'm going to be left with 0.25%, right? Now that I'm left with 0.25, which is 25% of the drug, that 25%, after another 2 hours, half of that goes away, right? So the 2 hours making a total of 6 hours, plus 0.125, that's half of 25%. Remember, this is the fraction of a total amount. It takes 2 hours for 50% of whatever is left to go away. Half-life. So we started with all of the drug, 50% went away in 2 hours, we're left with 50%. Out of that 50%, half of that went away within the next 2 hours, we're left with what, 25% of the original. And out of that 25%, half of that went away. In the next 2 hours, we're left with 12.5% of the original. So our answer here, we didn't need the formula. It was more conceptual. It's 12.5%, right? None of the others are right. Okay, so let's move on to our last and final question. How much work is done by a healthy individual who performs heavy exercise for 1 hour? how much work is done. Now, anytime you see work done, is just start thinking energy. They've given us a nice, they've given us a nice equation here for energy. But this is an equation I would say you should memorize for the MCAT. Energy is equals the power multiplied by the time, right? So now that we know this, it said the individual who performs heavy exercise for 1 hour, we need to figure out what is the power of that individual who's performing the exercise for, right? Clear my drawing so I can draw this. 1 hour, I draw my line, and I'm estimating it's probably like, it's close to 180, so I'm just going to use 180. It's always, when it comes to MCAT, you always estimate. So our power is equal to 180. Our time is 1 hour. But remember, you have to always convert your units, right? So if I convert my units, 1 hour is going to be 60 minutes, which is going to be 3,600 seconds, right? So then my work done, which is the same as the total energy expenditure, it's going to be my 180 watts multiplied by 3,600 seconds. I'll round this up to 200. And just to make it easier on myself, I'll round 3,600 down to 3,500. And this is an unspoken or written rule that I have, that if I round something up, I have to round the other thing down. And I only do that when there's this multiplication or addition. I don't do that when there's division, right? Because if it's division, if I round the denominator up and I round the numerator down, I'm pushing my answer further away from the true value, right? But I just have this thing. So I rounded it up to 200, round this down to 3,500, because I made it easy for me because I know 2 multiplied by 35 is worth 70. Now I add my zeros, right? And this is going to be true, sorry. All my answers are in kilojoules. So kilo beans, I divide by 1,000. And what I have is 700 kilojoules. 700 was very close to 80. And so that becomes my answer, right? 680 joules. Perfect. So with this question, my green flags were power, was the time, was the fact that I even had the formula in the past. But even if I didn't have the formula in the past, it's a formula that I'm expected to know from the MCAT. So depending on whether you recognize that total energy expenditure was the same formula you had to use or not, it's going to be either a red flag or a green flag. But you have all the information you needed, and you just had to estimate the power from the graph, right? All right, so thank you very much. I hope you learned something. Give me your feedback. Let me know what went wrong, what was confusing. I'm happy to help you with any and everything. Have a great rest of your night and see you in our next video. It's probably going to be the practice is on 4, but let's see, depending on what people say, I might do a last passage of the practices on 5. All right. Okay, stay blessed.